We're on air.
We are on air. Welcome, everyone, or hello, space fans. Welcome to our third episode on dark matter. We've been slowly going through the different types of evidence and detection methods and going over what exactly is dark matter, this ominously named subject in the universe, which makes up 85% of the mass of our universe. So the stuff that makes up you and me is not all that much compared to what's out there. But before we get too much into that, I do want to introduce our amazing expert. As always, joining us is Katie Mack from Melbourne, Australia. How you doing, Katie?
Good. How are you doing?
Good. I took a long nap today, so like without meaning to. I set my alarm, and then my phone died. So I took a
Nice.
2.5 hour nap instead of a 45-minute one. So I'm gonna be awake all night. So yay! It's gonna
Oh,
be great. How are you feeling now that I know a lot of we've had a lot of people mention that we've taken a break is because you've been traveling
yes.
around the world. How was your
I have
travels?
been traveling. I have been traveling literally around the world. I went to the Science Foo meeting at Google, which was pretty awesome.
And I hate you for
And
that.
then,
I mean, I love
yes,
you, but yeah.
yeah. And then I went to London and I worked with a colleague there and I gave some talks and I went to a science fiction convention. And then I went to Sydney and Canberra to present about dark matter and dark energy for National Science Week in a show that included an astronaut, which was pretty awesome. So that was
Yes.
so I got to meet and hang out with Commander Hadfield, which was awesome.
See, like I was all super proud that I've hung out with astronauts, and then you're like moving up the ranks of astronauts. So now I need to hang out with Hatfield sometime.
He's a great guy. He's really
He,
cool.
from what I've seen, he is an amazing human being. So I am quite jealous. And then you just got back, what, a couple days ago, right?
I got back Monday. Yeah,
Monday.
I've been kind of doing all the sleeping this week that I didn't do for the last 3 weeks,
Right. And,
which
you
has
know,
been
as you
which has been
should.
good. Yeah,
You
I
know,
kind of needed it. Yeah,
being healthy helps.
yeah,
So
yeah.
I've linked out there to the event page and on Facebook and Twitter and stuff like that. So this is our third episode. So you don't need to have watched the first two to understand what we're talking about today, but it will help color your understanding of where we're at. So we've gone over what dark matter is, how it was discovered, how does it compare to normal or baryonic matter, the evidence for it in WIMPs versus machos, and how much of it is believed to exist. So today, to start off, we're going to go with Katie's favorite subject in the world, which is MOND, or modified Newtonian dynamics, and why. A reason why I have a Saint Sagan candle here to to ward off things that might not have as much evidence, but there are a lot of people that find it compelling. So, what is MOND, modified
Okay.
Newtonian dynamic, and why are you skeptical of it? And what evidence is there to have for other hypotheses for explaining dark matter?
Okay, so modified Newtonian dynamics (MOND) is an idea to try to explain away what we see in the universe without dark matter, or with less dark matter, or somehow by modifying gravity instead of having most of the matter in the universe be dark. Um, Before I get into that, I want to just remind everybody what I mean by dark matter and what dark matter is, in case people didn't see the previous episodes. So, so dark matter is really invisible matter. So, most of the matter in the universe, as far as we're aware, does not interact with light. So it doesn't emit light. It doesn't absorb light. It's invisible, but it
Right.
does interact via gravity because it's matter, and matter has mass, and that mass is what creates gravity. What how things interact with gravity. So we know that there's more gravity in the universe than the visible matter we see can account for. Um, and so the way that we, for the most part, the way that we interpret that is that there's some kind of matter out there that's most of the matter that doesn't interact with light, so we can't see it, but it's creating this extra gravity, this extra gravitational force. So there's some people who say, well, why do you need a new kind of matter? Why do you need a new kind of particle or whatever? Maybe you've just misunderstood gravity, and it's really that the stuff you see has more gravity than you thought. So this is the whole idea behind modified Newtonian dynamics, and this paradigm has been used to try to explain galaxy rotation curves. So this is galaxies. Are, like if you have like a disk galaxy, the stars rotate around and they move faster than they should based on the amount of mass you see. So basically, like if there wasn't more mass holding everything together, then the stars and the gas at the outskirts of galaxies should just be flying apart and like flying off into the universe. And so galaxies are rotating too fast. So we know that there has to be more matter, or at least more gravity holding everything in. And so the Mond people say, well, maybe you can explain that just by saying that the stuff we can see has more gravitational pull, so like the bulge of the galaxy or whatever is holding on to those outskirts stronger, and so there's the force of gravity isn't just the sort of standard Newtonian idea that's like an inverse square law. There's some additional term, so that concept explains certain. Can be used to explain certain observations reasonably well. So you can definitely look at a lot of disk galaxies and say use this different force law instead of the normal Newtonian or relativistic force law, and then get the right answers basically for the way things are moving around. But it doesn't work for most of like larger scales. For other places we see evidence for dark matter. So we see evidence for dark matter in lots of different places. It's not just the rotation of galaxies. We also see evidence for dark matter in gravitational lensing, where massive objects bend space-time and light moves in these curved paths, and so we can see evidence for a lot of matter being there by how much lensing there is. There's evidence in the patterns we see in the cosmic microwave background. So this is the sort of leftover light from the Big Bang has these sort of little ripples in it, and when we look at how the ripples are laid out, we can see that there has to be some kind of matter that doesn't interact with light, some kind of pressureless matter, something that doesn't collide with itself, so non-collisional matter, which we think dark matter is. That has to be there for the cosmic microwave background to look the way it does. There's also the growth of galaxies early in the universe. It's hard to get galaxies to grow without having some sort of extra glue pulling everything together. So if you just try to throw a bunch of matter together, it collides, it heats up and bounces off, and you have this pressure. And so it's hard to get galaxies to form just through gravitational collapse if there's this pressure. But dark matter doesn't feel
gravity in itself is a really, really weak force compared to the other three forces. Yeah. It's extremely weak.
Yeah, so like when you collide things, they bounce, they heat up, you get friction, all of that. Dark matter doesn't collide. I mean, so the electromagnetic force that is responsible for being able to see things, because that's electromagnetic waves.
Right.
Dark matter doesn't do that, and that's what's responsible for letting you touch things. So this thing where if you touch something, it's really the electrons in your hand pushing against the electrons in the other thing that's allowing you to like push against something.
So I've really never given you a hug ever.
No, it's just but there has been electricity.
True. There was that electricity.
But yeah, so there's so it's electricity basically that allows you to push against things. It's electromagnetic repulsion. And if dark matter doesn't feel the electromagnetic force, if it doesn't interact with light, if it doesn't interact with photons, electromagnetic field, it can't collide. It can't push against things. So dark matter just passes through stuff. And so if you collide, for instance, two clusters of galaxies, then all the gas and dust and hot plasma and everything in those clusters of galaxies will get stuck in the center because it'll collide and heat up and everything, but the dark matter will pass right through. So,
Right.
so this is one of the ways that we know MOND can't really work. So there's this one galaxy cluster collision that's been called the smoking gun of dark matter.
And it just happens to be like the best name for the smoking gun.
Yeah.
And
Yeah.
before we get there, I wanted to hit on something real quick too.
Yeah.
Is that this is a very important concept when it comes to science. There's great. Look for different hypotheses, different explanations for what we see around you, but it needs to fit all the data. It needs to fit all of your observations. Yeah. You can't just cherry pick like we see in other things going on in our world that happens to be contentious with science, climate change. That you can't cherry pick your observations. That it needs to fit everything that's going on. And though it might, you might be able to explain one aspect of this, which happens to be the rotation curves of galaxies, it needs to also be able to fit these other observations we have. And if it doesn't, then it's not a viable option until you're able to somehow explain that as well and still have everything fit together.
Yeah, so, I mean, really this stuff is all about, like, finding a model that best fits as much data as you've got, right? So, so there are models that work perfectly fine in certain regimes, and you can use them in those regimes. But if you have a model that works perfectly fine in that regime and also explains tons of other things, that model is better, right? So dark matter is the best model for explaining everything, all taken together, all of the different areas where we see evidence for additional gravitational interactions. But it's fine to say that MOND works in certain regimes, but it can't. You can't use that to say, oh well, because rotation curves work better with MOND, then there shouldn't be any dark matter. When you take it all together, when you look at it all in the big picture, the idea that dark matter exists and that there's some kind of particle that is that doesn't interact with electromagnetism, but does interact with gravity, that fits so many of the different pieces of evidence that that's a much more compelling theory.
Right.
So it's entirely possible that gravity is modified on some levels. We know that Einstein's gravitational theories can't be the sort of ultimate theory because they don't work well with quantum mechanics, and so we're going to have to alter it to work with quantum mechanics, and that's what the string theory people are trying to do. That's an entirely different story, but
completely different story. Which there's not enough time in the world to even get into string theory. But maybe someday I'll get some of my string theorists on here, and then I'll just pretend like I have any idea what they're talking about. Before we get into the bullet cluster, though, I want to ask a question here that's coming up in the Q&A app, and I will actually remind people too, since I didn't do that. We are on Twitter. I am Scientific Scott down here if you want to contact us there. Katie is at AstroKatie on Twitter. I have the Q&A app enabled here, so if you're on Google Plus or on YouTube, you can load that up. I see a list of questions over here that I can select as we're going through, and this one comes from Michael Jobin, and he's like, so dark matter has no electrons? That's a very good question. So what's that about?
Yeah, so electrons are a kind of visible matter. They're in the standard model of particle physics. We think that dark matter is a kind of particle that is not in the standard model of particle physics. It's some kind of particle or set of particles that doesn't do electromagnetism. It's possible that there are sort of inter-dark matter forces where different kinds of dark matter particles can interact, and some have suggested dark matter atoms. That's difficult because if you do that, then you have to deal with the fact that you then get a collisional kind of material, which is not useful. There are some ideas, there's some sort of models that have certain kinds of inter-dark matter forces that do work. There are certain kinds of what's called atomic dark matter, where you have dark atoms, where you have sort of different particles of dark matter that get bound together. But again, there's sort of certain problems with those models, and it gets a little complicated. But yeah, there's no, I mean, dark matter doesn't. There's no reason to believe that dark matter has the same kind of particles as we have in regular matter, and certainly an electron would not be dark.
Right. Awesome. All right. Thank you for that question, Michael. And then let's get over to that smoking gun. That is the bullet cluster, which I think is awesome. It's just so cool that it's called the bullet cluster as well.
Okay, so I'm gonna do a little screen share to show you this.
Yeah.
I don't do screen shares very often, so hopefully
no, you
this will
don't.
work well.
So we're going to new territory here, but it works great.
Okay. Okay, so this is the bullet cluster.
Yep.
And it is called the bullet cluster because, can you see my cursor, by the way?
I do see your cursor, yeah.
Okay. So it's called the bullet cluster because it's two clusters that have collided with each other. So there's this cluster here, which is kind of hard to see, and then this little cluster here.
Right.
So they were on opposite sides. They collided, and if you look at them in X-ray light, you can see this gas in the center. This gas is the gas that was in each cluster individually before the collision.
Right.
So all clusters of galaxies have hot gas that glows in X-rays that makes up actually most of the visible matter in the cluster. The galaxies themselves are not that much of the mass. Most of the visible matter is in this X-ray gas by like a huge factor. So like 80 to 90% of the visible mass in the cluster is X-ray emitting gas. So
and why is it because there's so much heat and energy going on during its collision that it's excited to that much that we wouldn't be able to see it with our eyes, or why is it emitting an X-ray?
It's emitting an X-ray because it's, well, I don't know, because it's the temperature to glow in X-ray gas, in X-ray light. I mean, all clusters of galaxies have this really, really hot gas, and it doesn't emit a lot in the visible light. The stars are dominant, are brighter, but the gas can be seen with X-ray telescopes, and so you get this glowing. And all galaxy clusters have some kind of gas in them, or most anyway, and so they usually have what's called the intra-cluster medium.
Okay.
So the reason that this is called the bullet cluster, of course, is because that sort of sort of V-shaped bit there, that's where the little cluster punched through the big cluster and left this like shock in the X-ray gas. Yeah. So you see that there's the big cluster over here and the little cluster over here. The galaxies have passed through because the galaxies are far enough apart that they don't tend to collide with each other. They just kind of pass each other by. But the gas that was in each cluster got sort of stuck in the middle because it collided, it heated up, and it got really hot in this, and to be glowing with X-rays really brightly. And it got all stuck in the center of the clusters, and over time, it'll sort of drift back into where the clusters it started with. But at the moment, it's all sort of clustered in the center like that. So if you were to so if we were to guess like where all of the gravity, like where most of the gravity in this cluster should be, based on seeing this image, we would guess that most of the gravity is where most of the mass is, and most of the mass, based on the visible matter, is in where that X-ray gas is. So you would guess that the gravitational field would like peak in the center, or like sort of distributed where that bright red, the X-ray gas is.
Right.
And there is a way to measure the gravity in this cluster, and that's to look at distortions of the galaxies in the background, because you have gravitational lensing. It's called weak lensing, where it just very slightly distorts the shape of all these little tiny galaxies in the background. And so you can look at the shapes of all the little tiny galaxies in the background, and on average, that'll give you an idea of where all the mass is. And so if you do that, and you color in where most of the mass is, based on like where most of the gravity is, where most of the lensing is, you see this. And so this is just a sort of coloring in. This is not an image, but this is using blue to highlight where most of the mass is. And what you see is very clearly, the gas is in one place and the mass is somewhere else.
Right.
And so there really shouldn't be that much mass where the galaxies are, because the galaxies, as I said, are a really small fraction of the mass of the cluster in terms of what we can see. But what this shows is that there is dark matter. There is some huge amount of matter that passed right through during that collision, that didn't get stuck in the center.
Right.
And so if you look at it together, you can see that there's a real separation between where most of the mass is and where most of the visible matter is, right? And so that's a really crucial result, because you can't just say that the visible matter has more pull, because if that were the case, then most of the gravity would be where most of the visible matter is.
Right.
What you see is that there's something that you cannot see that has more gravity than the visible matter. And so that's dark matter. And so that shows us that there is a non-collisional component of the matter. So there's something that we can't see that doesn't have collisions, that is in a different place. It's actually separated from where most of the matter is. And that's like really good proof that dark matter is a real thing separate, because you can't use just modified gravity and say, like, yeah, so all the visible matter we see is over there, but then it sort of pushed its gravity somewhere else. Like, that doesn't work.
Right.
So I'm gonna unscreen share now.
Yeah.
So that's one of the most compelling pieces of evidence for dark matter being a real thing, is this situation where we've been able to see dark matter and regular matter not in the same place at the same time. I sometimes call this the inverse Superman problem. Like, how Superman and Clark Kent, they're never seen in the same place at the same time, so you can tell they're the same person. Well, in this case, we have, dark matter and regular matter are usually not seen in different places, because they're attracted to each other, because they both have gravity. But if you can actually separate them, you can tell that they're actually different things.
Which actually pulls up with a question here. We have the Q&A app. This is by Romain Falio. I am sorry if I completely ruined your name. This is can matter and dark matter cohabit in the same space?
Yeah, they totally can. There is probably dark matter passing right through you right now. Lots of it.
Or Taco Bell, one or the other.
Every time I bring this up, somebody makes that joke.
Hey, it's what I'm here for. I am here for cheap jokes.
Yeah. Anyway, yes, so dark matter is probably passing through you right now. It's passing through the Earth. In the centers of galaxies, there's a lot of dark matter. There's a lot of regular matter. They don't really interact that much except via gravity, so they can totally be in the same place. I mean, if you look on the sort of microscopic level, if dark matter is made of particles, those particles might occasionally, collide with regular matter particles or with each other, but it's really, really, really rare. So for the most part,
in previous episodes, we talked about detection and why it is so difficult to detect it, because it doesn't interact with normal matter in the way that normal matter interacts with each other. So we are running long, and I think it's okay for right now because we only get one topic of our 3 today. But we did kind of chit chat for a little bit in the beginning. So let's move along to we were talking about these galaxy clusters, then going on to the cosmic web, which is an even larger view of our universe using these galaxy clusters. So what is the cosmic web? And we're going to look at some really pretty simulations, but what do these dark matter only simulations show us?
So you can do simulations of of just dark matter particles, where all you include in these simulations is gravity, and in those simulations you can show how dark matter comes together and forms these beautiful web-like structures just through gravitational collapse. So if you start out with a distribution of particles that's pretty close to uniform, and then you allow that to evolve over time through gravity, any place where there's like a little bit more matter over here, stuff will be attracted to that. and you'll
Right.
make like a cluster, and then things will be stretched out along filaments, and you'll get this web-like structure, which is really beautiful, and that is sort of is like the backbone of all of the structure we see in the universe. So there's
So I'm going to screen share real quick a video that was made by Illustris, which is one of worked with the who I work with, the Space Telescope Science Institute, and some other people, going over some data that's been collected. And this is a simulated time lapse from right after the Big Bang, and showing how dark matter, plus also it's going to be showing some gas in here as well, but it's showing us how the dark matter is coalescing over time. So you can see on the
right.
bottom the timeline as we're going in billions of years.
Yeah, so you can see in that image that things are coming together in clusters, and there's this sort of web-like structure that you see that like develops just naturally over time as everything comes together. So it's kind of a neat thing to see that all come together. Of course, this video also has, as you can see, the
Explosions
gas, and you get
of
these
gas.
little supernova explosions. So now it's sort of focusing on the gas, but that sort of that whole structure is based on this kind of dark matter backbone, so to speak.
Right.
Let me actually show you another picture, which is like a piece of a dark matter only simulation that shows that structure also.
Beautiful.
Hold on a second.
And while you're pulling that up there, I'm going to go and check some questions here as well. Okay. I am seeing a lot of activity on Twitter. Thank you for all the retweets, everyone, and getting our show out. And yes, I love this. This is like my favorite. This is like the background on so many of my devices right now. It's hilarious.
Yeah. So this is so here you can really see that cosmic web structure, and you see that there's clusters and these filaments, and galaxies kind of form where the sort of overdensities, the concentrations of dark matter are. And so then you have these big voids where there aren't a lot of galaxies forming because there's not a lot of matter there to pull everything together. Right. And then you have the things sort of forming. And this image that I'm showing now is just dark matter. So this is from a simulation that just does dark matter, and the colors are just density. And so you can get all of this structure just from looking at the density as things come together through gravity. So it's really neat to look at.
It is
and
neat
that's
to
called
look
the
at.
cosmic web for obvious reasons.
Right, and actually I have a question here from Twitter, or not Twitter, but from YouTube. This is from Katie Stoka, one of our regulars. So, hi Katie, thank you for this question. I was going, hi Katie and Scott, what is between the cosmic web? It looks like just empty space, and why do the gaps not have more of the cosmic web in them?
So it's sort of just a property of gravitational collapse that you get voids where there's just very little matter, and if it's a very low density region, then any particles inside will be more attracted to, they'll be a little bit closer to one of the filaments on the edge, one of these sort of walls of the void, and it'll move in that direction. So you get sort of naturally these regions just emptying out, and there's very little there. And so in the voids, there's almost no structure. Occasionally, you do see things in the void sometimes as things sort of move around, or maybe there's a little pocket of matter there, but for the most part, the voids empty out and things get pulled toward the clusters and the filaments over time.
Awesome. And let me see here. So I'm going through the Q&A app, which again, there's some really good questions, and some of them we actually will have to answer because they're more relevant to our next episode. But let's see here. This is from TPC World. Could there potentially be dark antimatter?
Yeah, so this is an interesting question. There are some theories in which dark matter particles are their own antiparticles. So there's antimatter is like regular matter, but it has an opposite charge and an opposite spin. And if you have a particle of dark matter that doesn't have any charge, then there's the potential for the antiparticle to be the same thing. And if that's the case, then you can get annihilation, where two dark matter particles that are the same kind of particle come together and they annihilate because they're also antimatter of each other. So it's possible that dark matter has antimatter particles that are different kinds of particles, but it's also possible that dark matter is its own antiparticle, which is kind of a crazy concept.
Right, that is kind of a crazy concept.
Yeah.
So we might have to dig into that idea a little bit further on. So
Okay.
with the cosmic web here, so what we're really seeing is that because there is so much dark matter in the universe, that's what is allowing this structure to happen, right?
Yeah.
It's not because if we didn't have that dark matter, let me put your screen back up. If we didn't have it, we'd be seeing a completely different way that what we're looking here are what, in millions of parsecs or hundreds of millions of parsecs wide?
Yeah, I don't remember that image exactly how big it is, but yeah, it's a huge number of, it's like millions, several million light years or something, I think.
Right. So we're looking at huge scales.
Yeah.
And when we're like zooming out, if we didn't have that dark matter there to really bring all that together, our universe would look completely different. We would have a completely different structure.
So it would take a lot longer for galaxies to form if they had to not only come together by gravity, but also dissipate all the energy of those collisions when the matter comes together. So the fact that the cosmic web can form and can form quite early allows galaxies to form early by pulling matter in, and the cosmic web can form without having to worry about collisions and stuff because it's just dark matter. It doesn't have pressure, so it can form these beautiful filaments and clusters and be like sort of the sort of seed for the formation of regular matter objects.
Awesome. And so to blow our minds as we're leaving here, I am going to show you all an image of all of the dark matter in the universe.
I love this picture.
All of
this
it.
is one of my favorite pictures.
You ready for your minds to be blown, people? This is all of the dark matter in the universe right here. This is taken from Planck.
Yeah. Yeah, so this is a cool picture. So what you see here, this is a projection of the whole sky, the entire sort of all directions view. And the gray stuff in the middle, that's just masking out where the galaxy is, where our galaxy is, the disk of the galaxy. So this projection is such that the top and bottom are looking directly away from the disk of the galaxy, and the middle is where the disk of the galaxy is. And what you see is they've used the Planck satellites maps of the cosmic microwave background, and they've cross-correlated it with, I think, some infrared survey or something like that. Mm-hmm. And what they've done is they've showed using how what they're looking at is gravitationally lensed, and using what they know about where the sort of big clusters of galaxies are and stuff. They're mapping all of the dark matter in the universe. It's like all of it. Yeah, that's all of the So what they're saying is that if you look in a particular direction where this is colored, white or blue, that's telling you that one of those directions has a lot more dark matter than another direction. So it's a really neat picture, because you're able to really see, like, if you had dark matter vision and you could look out into the sky.
I want dark
that's
matter
what it
vision.
Like.
I want dark matter vision.
Yeah, it's really cool.
So we have many different ways of knowing that dark matter exists. No, not just from the observations of the rotation rates or gravitational lensing, but we can, just by looking at the way that the structures of our universe is set up, it has to be there. And now we're working, and we'll be getting into this next time on newer research, including Katie's research, on how we are trying to better understand what it is and how we can really, really detect what's going on there. Because now we get into more particle physics than into large-scale cosmology, or where the two combine, where we're taking the extremely small and the very, very large and finding out where they meet to explain our universe.
Yeah, so I'll talk a little bit about like what dark matter did in the early universe and how the particle physics of dark matter can be relevant to these big questions.
Yes.
That's what I work on.
So I'm going to hit a couple questions before we go. One of them is going to be pretty easy to answer, but this one's from Patrick Calhoun. Is dark matter dangerous to us?
No. No, so dark matter it passes through you. It doesn't interact with you. It doesn't collide with stuff in your body. Like I think, maybe once in a very long time, one of your particles will get like bumped by a dark matter particle via some interaction with the weak force, but it's not a problem at all.
So can I blame my bad moods on a little bit of dark matter going?
Maybe. I mean, I think that you probably get interacted with by dark matter about as much as you get interacted with by neutrinos, and it's just not very much. So they're fine. They're not going to hurt you. They're not. Yeah, they just sort of have gravity and they pull things toward them.
Cool. And the last one here that I want to hit on with the Q&A app is from, again, Michael Jobin, which is not a question, but we have infallible evidence that Mack is cool. So you have it here from the internet, folks. Mack is cool, and I do agree, not just because you're my friend, but you have brought so much insight in this series so far in helping many people, myself included, understanding what's going on with dark matter. Our next episode is going to be 2 weeks from today, where we're going to be getting into signs in the early universe, as I'm looking over at my list of everything, because I prepare for stuff. It's crazy. So we'll be getting into signs of the early universe. And let's see here, obliquely refer to baryon acoustic oscillations. So we will explain that in English on what we'll be doing. Yeah. And then also be getting further into Katie's research. So I do want to thank all of you that have been giving us questions, tweeting us out on over on Twitter, all the questions on YouTube. We will be back in 2 weeks, unless you're like, are you traveling some more?
No, I'm in Australia like until December, I think. Like I'm gonna be in one place for a really long time.
Awesome. So we will be back in 2 weeks from today to be able to go over more than that. If you guys have any more questions, please let us know in the comments below here on YouTube. You can still use the Q&A app. I will try to check it later, but since we're going to be off air, try to either hit us up on Twitter. Again, I'm at Scientific Scott. Katie is at Astro Katie. We try to answer the questions a little bit afterwards as well. And that is it for today. So I do recommend to catch up on our previous 2 episodes, plus this one. We will have our 4th, and then we'll be moving on to some more awesome subjects, because we've done what? Supernovae. We've done neutron stars. So we try to keep it awesome here with really interesting topics. So if there's anything that you want to know about the universe, let us know, because your questions really do inspire new episodes coming out there. So we do thank you all for that. So go ahead.
Check out the whole series. I have a playlist somewhere. I'll tweet that out. You can also find it on my webpage, astrokatie.com, under the outreach and speaking section or something like that. So check out the other videos, and it'll be fun. We'll see you next time.
Sweet. All right, everyone. Thank you all for watching, and as always, keep looking up.